So next we will learn more about LTE Advanced. In this section, you will be getting an overview of some of the features that have been introduced in LTE Advanced by 3GPP. LTE Advanced um, extends the capabilities of the first LTE that was released in release 8 and 9 by introducing some new features. Namely, some of these features are carrier aggregation, enhanced multi-antenna techniques like single-user MIMO and multi-user MIMO, coordinated multi-point operation, or which is abbreviated as COMP, and enhancements to UE categories. We will go through each of these in this section, except for this one where the single-user MIMO and multi-user MIMO were discussed in a previous section on multiple antenna techniques. So before we delve into the different enhancements, let's look at this chart. This may look familiar from one of the previous lectures. So as we know, LTE was released in release 8, which was the first official LTE release, and then came along release 9 about a year later. 3GPP was continuing to work and evolve LTE to meet the ever growing demands of data and fast throughputs. So they came up with uh, these three releases, 10, 11, and 12, in this time frame to further enhance the capabilities of LTE and offer new features that would be able to cater to the ever-growing demand for data and fast speeds. So starting off with the first new capability that was introduced in LTE Advanced, let's talk about carrier aggregation. So LTE release 8 or 9 specified system bandwidths of 1.4, 3, 5, 10, 15, and 20 megahertz to meet different spectrum deployment requirements. Support for wider bandwidths up to 100 MHz was one of the distinctive features of IMT Advanced systems. The IMT Advanced systems targeted peak data rates in excess of 1 gigabit per second for low mobility and 100 megabit per second for high mobility scenarios. In order to support wider transmission bandwidths, LTE Release 10 introduced the carrier aggregation concept, where two or more component carriers with arbitrary bandwidths belonging to the same or different frequency bands could be aggregated. So let's spend some time to understand what was conveyed in this paragraph. So if you remember from an earlier lecture, LTE offers network operators a great deal of flexibility when it comes to deployment of frequencies. And the way it does that is it specifies that you can deploy a LTE carrier in bandwidths of 1.4, 3, 5, 10, 15, and 20 megahertz, depending on how much spectrum you own, right? And again, you can either have a frequency division duplex or you can have a time division duplex. Carrier aggregation is supported in both FDD and TDD. So previously, prior to LTE Advance, you could only have one LTE carrier or LTE frequency um, serving users. But with carrier aggregation, say you had two chunks of spectrum that you own in a given market and you want to use both of them for LTE. So prior to LTE Advanced, you could run LTE independently on those two frequency spectrum pieces. What LTE Advanced offered you was that now you could use those two chunks of spectrum as one and use them as an aggregate or together. So that's what's implied by carrier aggregation in a wide sense. And it was devised to meet the specs laid down by IMT. Um, and IMT is a body that works in conjunction with 3GPP to define specs and requirements for cellular systems. So they had laid down a requirement of data rates of 1 gigabit per second for low mobility and about 100 for high mobility. So the carrier aggregation is able to meet those demands, and how it's able to meet that we will see in a little bit here. The other advantage of carrier aggregation is that it enables operators to use different chunks of spectrum in combination to deliver greater throughputs to UEs. So it enables network operator to use fragmented pieces of spectrum, since not all operators are spectrum rich. So we talked about, right, a operator can have multiple chunks of spectrum which can be in the sizes spanning from 1.4 all the way to 20 megahertz. And different operators, you own different kinds of spectrum, right? Not everybody has 20 megahertz, not everybody has 1.4. So with carrier aggregation, you could have one LTE carrier on, say, 3 megahertz, um, and another LTE carrier on 15 megahertz. And then you can use that as one big LTE carrier and deliver faster speeds to your users. Operators can use up to 100 megahertz of combined bandwidth, which is huge. Given that 100 megahertz is like combining five 20 megahertz LTE carriers. And so roughly on a 20 megahertz carrier, you can get up around 300 megabit per second max speed. So imagine if you had five of those, right? You are already at 1.5 gigabit per second of throughput, which is pretty huge, right? So that's the advantage of carrier aggregation. So now carrier aggregation can be deployed in three scenarios here, and we're going to walk through each of them, um, and we'll get a better sense of what they mean. So in the intra-band contiguous carrier aggregation, and then so what this means is, say you have one frequency band which is pretty big by itself, say it's 40 megahertz in total bandwidth. Now, you can only go up to 20 megahertz of one LTE carrier in LTE as per 3GPP. So, in order to use your 40 megahertz, you would have to chop it up into two parts of 20 megahertz each, and they have to lie in the same band. So you could run carrier aggregation and use those two LT carriers that are side by side with each other, and this is called intra-band contiguous carrier aggregation. Contiguous mean they are continuous within the same band, and intra-band mean they are part of the same band. Then you can have another setup where you have intra-band non-contiguous carrier aggregation. So this would be a scenario where, say, within the same band you had 40 megahertz, but and you were to chop it up into two 20 megahertz carriers, but those carriers are not alongside each other. They are kind of spread apart. So you could still do carrier aggregation, but in this case it would be called an intra-band non-contiguous carrier aggregation. The third setup is called interband non-contiguous carrier aggregation. This would be in a scenario where, say, you had two bands, frequency bands, and there were two carriers, and you wanted to do carrier aggregation. In this scenario, you would have interband because it's two different bands, and there are two carriers that you want to use. So that's the setup for the interband non-contiguous carrier aggregation. So this picture shows you these three scenarios. So the intra-band contiguous carrier aggregation is where you have one frequency band called A, and you have two component carriers, and they are side by side with each other. And you can use CC1 and CC2 as two LT carriers, uh, and you can aggregate them together. So that's intra band for you. Say you had one frequency band and you had two component carriers, but they are not you know they're not butting up against each other. You could still use CA, but in this case it would be called an intra-band non-contiguous. Non-contiguous meaning they have some frequency separation. And the third type is called interband non-contiguous carrier aggregation, where your component carriers are actually distributed between frequency bands, and you can still do CA, but this would be an interband. So, and again, each of the component carriers can be any of these bandwidths: 1.4, 3, 5, 10, 15, or 20 megahertz, depending on how much spectrum you own in that market. So this is just a pictorial way of showing how you would deploy carrier aggregation in your network. So let's look at scenario number one, where we have two frequencies, FC1 and FC2. And FC1 and FC2 are two frequencies with similar coverage. So think of it like they are low band frequency spectrum where the propagation characteristics are pretty similar. They cover the same amount of area, and you have this region where you have multiple E node Bs at this location, and each of these E node Bs has three sectors, and these disks here represent the coverage of that each sector, and these colors represent coverage from each frequency. So the dark gray is the coverage from FC1, the light gray is FC2. So the coverage is similar in this aspect, whereas in this scenario it's the same setup, but FC1 and FC2 have a different amount of coverage. Say you can have FC2, which is the light gray color, has a lower coverage compared to the dark gray, which is FC1. And this can be due to, say, your FC2 was a higher frequency. So say FC2 is a high band frequency spectrum, say 21 megahertz, whereas FC1 is more like 800 megahertz. So obviously we know that 21 megahertz doesn't propagate that far. The path loss is higher. So in that case, the coverage from AWS or 2100 megahertz would be less. So this is that kind of setup. So you can have CA in both of these setups. You can have so in these disks you would get um, carrier aggregation from both FC1 and FC2 in this scenario, whereas in scenario 2 you would only get CA when you are in the overlapping coverage. So when you are in the light gray, you would be able to get carrier aggregation from both FC1 and FC2, whereas if you are in this region, the dark gray, so you are covered by FC1, you are no longer in the coverage of FC2, you will not get carrier aggregation.